Okay, so now we're going to do problem 2 from chapter 11. Now this problem says that an automobile traveling at 80 kilometers per hour has a diameter that's 75 centimeters it's traveling 80 kilometers per hour, has tires of 75 centimeters in diameter. And what is the angular speed of the tires about their axles? And if the car is brought to a stop uniformly in 30 complete turns, so 30 revolution, it comes to a complete stop. And you're asked to find what is the magnitude of angular acceleration, and also what is the angular speed when it brought to a stop, and how far does the car move during the braking. So this is, you're given the linear velocity, you're given the diameter. So in order to figure out the angular velocity, it becomes very straightforward, because we know that omega and velocity, they differ by this. So omega is equal to V over R, okay, and R is the radius. You're not giving the radius, you're giving the diameter instead. So we can actually calculate the diameter first. We can calculate radius first. So your R is simply d over 2, and then convert it to the SI unit. You should have 0.375 meters. So that's your radius. Now what about the velocity? The velocity is also not given in SI units. You need to convert that to SI units. So your velocity is 80 times 1,000, converted from kilogram to converted to kilometer to meters, and an hour becomes seconds when this divided by 3,600. So the velocity that you have is 59.3 meters per second. So you have the velocity, linear velocity, you have the radius. So we're ready to calculate what is the angular velocity with this magnitude. So you have 59.3 over 0.375. So when you do the calculation, you have the angular velocity that has a unit of, the velocity, sorry. The velocity is, after you do this, that's 22.22. All right, so let me just go back. So this is 22.22 and divided by 0.375. So your answer should be 59.3. And that's in radians per second, okay? So this is the angular velocity, and it says that after 30 turns, after 30 revolutions, it comes to a stop. So when it comes to a stop, it means that the final angular velocity is 0. And you also find what is the angular acceleration. So if you look at this, this is a counterpart of linear velocity. For rotation, this is a displacement. So you have the displacement, you have the angular displacement, you have the angular velocity. So it becomes easy to calculate angular acceleration, because we can just use this equation. You have omega, the final velocity square, angular velocity square, is equal to initial velocity, angular velocity square, and then plus 2 times the angular acceleration times the angular displacement. Okay. Now it says I makes the 30 revolution. What does that mean? 30 revolution. Each revolution is 2 pi radians. So this is altogether there are 60 pi. Angular displacement. So we have this is 0, and initial angular velocity is so this would now be our initial angular velocity, which is 59.3 squared, and then plus 2 times alpha, and then times this. This is 60 pi. 60 pi, so it's 60 times this, 3 times pi. So after you plug in these numbers, you should get alpha, which is negative, because you asked to slow it down. So your alpha is negative 9.3 radians per second square. Okay. So that's basically how you do it. Now, the theta, of course, if you multiply them out, your theta, you should get a value that is 188.5, and that's in radians. Okay, and then you're asked to find what is the total distance in the linear sense for the linear motion. If the wheel has turned 60 pi, and each pi has each turn has 30 terms, and each term is is 2 pi. So you have this radians. So how do we calculate? How do we calculate the linear distance? If you know the diameter, or if you know the radius, of the wheel, then the linear distance, by definition, is just the radius of the wheel times the angular displacement. So you have your R. Your R is 0.375, and your theta. Your theta is 188.5. So after you do the multiplication, you will get 70.7 meters. Okay? Or you can just use common sense. It has 30 revolution. What does that mean, 30 revolution? For 30 revolution, and each is 2 pi r, because that's the circumference. So that's exactly the same thing here. So you have 60 pi times r, and then this is your 60 pi, and then times r. That gives you 70.7 meters. Okay, so this is a simple problem that that kind of demonstrate how the linear velocity in relation to the angular velocity, and how the angular displacement in relation to linear displacement. Okay. Now the next one we want to do is problem 5. All right, problem 5, let's see. A 1,000-kilogram car has 4 10-kilogram wheels. So the mass of the car is 1,000, and that mass of the car, of course, includes the mass of the wheel. And the mass of the wheel, which I'm going to use MW, is 10 kilogram. Okay. So when the car is moving, what fraction of its total kinetic energy is due to rotations of the wheels about their axles? So this is the car, and the car has 4 wheels. So let's see. So this is the car and has 4 wheels. So when this wheel rotates, this car is going to move. That's moving at a velocity v. So in other words, this wheel will also have the linear velocity that has v. So if you know the radius of the wheel, then you should be able to deduce what is the angular velocity of the wheel. Okay. Now assume that the wheels have the same rotational inertia as uniform disk of the same mass and size. So this is basically treat that as a disk, and all right. So let's assume that the radius of this wheel is r, little r here. Okay. So how do we do this kind of problem? Let's say, what is the total energy of the car? This car, the whole thing. Treating that as a system, it is moving with the velocity v and has the mass of m. So the total energy of the system would just be 1/2 mass of the car and then the velocity that is moving. Okay, so you have this. So you have the 1/2 m, mass of the car times v squared. Now, what is the energy associated with the rotational energy only? That's from the wheel. So let's say the kinetic energy, that just rotation for one wheel, that is equal to 1/2, and then the rotation inertia of the wheel, and then times the omega squared. Okay. Now, what is omega in relation to velocity? Because it's moving like this, so we know that omega would simply just be the velocity over the radius of the wheel. This is just for one wheel, okay? And it mentioned that we treat this wheel as a disk. What does that mean? It means that your I is simply equal to, your I has expression, let's see, 1/2 for a disk. For a solid disk, that's 1/2 mass of the wheel, and then times the radius square. Okay, so this is the rotation inertia of each of the wheel, and you have altogether there are four each one is moving. So this term should be multiplied by 4. So let's see what is the total. So the rotational energy, the total rotational energy should be 4 times this, right? This is for each one wheel. When you have four wheels, so this multiplied by 4. So this multiplied by 1/2 I omega squared. Then we want to replace our I with this expression. So that's what we have. So 4 divided by 2, so you got 2, and then your I here is 1/2 mass of the wheel, and then R squared. Let me just write the lowercase a little bit smaller. Okay, so this is your I, and then omega squared. Now omega squared, we're going to use this expression. Okay, so you have your V squared over R squared. So that's why you can see that these two, they cancel each other, because so that's why you don't need the information about the size of the radius. So what we have here is that the two divided, they cancel each other. So you have the mass of the wheel and then times V squared. Okay, so this is a total rotational energy when you take the 4 wheels into account. So you also find the ratio of this energy to the total energy. So what is the fractional? What is the fraction? So the fraction will be that you have the rotational energy coming, that's from the 4 wheels over the total kinetic energy of the system. Okay, so in that case, this one has the mass of the wheel, and then times V squared. And then in the denominator, our total energy of the system is just 1/2 mass of the car, and then you have V squared. So you can see that it doesn't really matter how fast the car moves, because the V basically get canceled. So cancel. So what you have here is that you have 2 times mass of the wheel over the mass of the car. So we're given those those numbers, so you can use that. So 2 times mass of the wheel is 10, and mass of the car is 1,000. So what we have here is that the fractional is 0.02, so it's 1/50th. Okay, so that's basically how you calculate. So you can see that when this car is moving, the only thing that matters is the ratio of the masses. And it doesn't really matter how fast it it goes, how fast it travels, and also the radius of the tires. Okay, so that's problem 5. And the next one we want to do is problem 7. Problem 7, and I'm going to draw a diagram first. So you have this. Let's see, that, and that. All right, so let's see. So this problem, this is a diagram for the problem. It says a solid cylinder of radius 10 centimeters and mass 12 kilograms. Start from rest. So the initial velocity is 0. Start from rest and rolls without slipping. So it is rolling. When it's rolling, which means that it has linear kinetic energy and also rotational kinetic energy. So rolling without slipping a distance that's 6 meters down the roof that is inclined at an angle that's 30 degrees. What is the angular speed of the cylinder about its center as it leaves the roof? Okay, so you have this. So it's just going to keep rolling, and then once it gets to that, it's going to fall off the roof. Okay, and so you're asked, what is the velocity, the angular velocity right here? Because this starts initially from rest, which means that the initial angular velocity is 0, and then you're asked to find, after you roll through this distance, what is the final velocity at that point? And then the edge the roof's edge is at height that's 5 meters. How far horizontally from the roof's edge does the cylinder hit the level ground? So this is going to roll off, and then it's going to trace out projectile motion. So you need to figure out what is that distance. The height is given. Okay? So how do we go about doing this? So from this point to that point, we know the distance that it traveled. So at the same time, we know that because if you define the gravitational potential energy to be here, if you define your gravitational potential energy to be 0 here, and then when at this position, it will have the gravitational potential energy that's mg. That's called that mgh. So this is the height, right? So what is our h? You have the L, that's 6, and then so h is just the opposite of the angle. So your h, let's find out what our h is. So your h is simply 6 times sine of 30 degrees. So you will get your h, that's 3 meters. Why do we want to know that? Because we want to solve this problem utilizing the conservation of energy. At this point, it's not moving. There's no kinetic energy, but there's a mgh energy content within that system. And when it rolls down at that point, we assume that there's no gravitational potential energy. So all the energy has been converted to kinetic energy. So that's how we are going to do that. So let's see. So if we define this, initially we have mgh because it's this height, and then kinetic energy, of course, that's 0. Okay. Now at this point, you have the final gravitational potential energy is 0. Then the kinetic energy, has two forms. One is rotation, and one is the linear motion. So I'm just leaving it as a K. All right. So we can solve equations like that. So you have initial energy that's equal to the final energy. Initially, you have your 0. That's from the kinetic energy plus mgh, and that's equal to. At this point, there's no gravitational potential energy, so you have, 0 gravitational potential energy. Kinetic energy, you have 2 terms. That would be the 1/2 mv squared, and then plus the 1/2 I omega squared. Because this thing is not just moving this direction, it also rolls. When it rolls, it means that it has the 1/2 I omega squared, the rotation energy, and then plus the 0 gravitational potential energy. So from this, we can see that you have this, the mass is given, height we already calculated, and the velocity. This is the final velocity, and then this is omega. So let's say, what is omega? And so you have the omega and v. They are differed by this, the radius. Okay, that's just a simple, relation. So you have. So what we need to do is that we need to calculate the I first. If we treat that as a disk, then your I is simply equal to 1/2 mass of the object, and then times the radius of the object. So let's calculate that. So you have 1/2 times 12, and then times 0.1. This is 10 centimeters, so it's 0.1 meters. And then, so what you have here is that your rotational inertia should have 0.06 kilogram times meter squared. Okay. So now we have this. You have your 12 times 9.8, and then times 3. That's equal to 1/2 times 12, and then times your v, because we are asked to find omega. So let's replace our v with that expression. So you have your omega squared, and then times your r squared, and then plus 1/2, and then you have your I, which is 0.06, and then times your omega squared. So you can see that we have everything in front of us. The only thing unknown is your omega. So after you plug in this and solve for your omega, you'll find out your omega is equal to 62.6 radians per second. Okay. So once you calculate your omega, you can actually plug this number to this equation to find the velocity at that point. So your velocity now is just omega times r. So then you should have the velocity that's 6.26 meter per second. Okay. So what it means is that this ball, when they reach at this point, it has a velocity that's 6.26 meter per second, and then it's going to go, it's going to go undergo the free fall, not free fall, but the projectile motion. So this is like you have an initial velocity that's pointing in that direction. So you have your v naught. So now we're going to treat this as your starting point, because after you roll off the roof, then this part is governed by the projectile motion. So let's say your v naught now is equal to 6.26. Okay, and what about the angle? So this is your angle. So your angle here is your 30 degrees. So you can express this initial velocity at that point that has a negative horizontal component, that also has a negative y component, and to figure out so that you have the initial and the initial velocity. So let's do that. So you have your v naught now is v naught xi plus v naught y j hat, and your v naught x is 6.26, and then times cosine 30, because adjacent to the angle. And then I hat, because it's negative, so it's negative. Okay? And then your y component is also negative. Now it's sine 30, and then j hat. So numerically, your horizontal component will have a value of negative 5.42 I hat, and vertically, it has 3.13 j hat, okay, in meter per second. Why do we need this information? We need this information because you're asked to find the horizontal distance. You have the horizontal velocity, so the horizontal distance will just be horizontal velocity times time. So we need to figure out the time information, and the time information can be obtained if we utilize the information from the vertical motion. Okay, so this is what we're going to do. So let's say we define our coordinates. Let's say initial height is at 5. The final height is at 0. So we can, and then it undergoes the free fall acceleration in the vertical direction. So in that case, we can set up equation and then find out the time, because we have yf is equal to yi plus initial velocity times time in the vertical direction minus 1/2 gt squared. Okay. Final height is 0, initial height is at 5, and your initial velocity is negative 3.13. So it's negative 3.13, and then times time, and then minus 4.9 t squared. So you can see that this is a quadratic equation. So after you apply the solution for the quadratic equation, your time, you should get 0.74 seconds. So once you have the time information, this is the amount of time for the object to go from this point to that point. So in the vertical direction, horizontally, then that will be, so what will be the x? Your x, if we just use the numerical value, in other words, just use the magnitude, that will be the horizontal velocity, which is 5.42, and then times the time, 0.74. So after you do the calculation, you will get 4.01 meters. Okay, so this is a cool example that the system started out with the linear motion and also the rotation, and then once they leave off the roof, then it's a projectile motion. And you can see that so for this part, we use the conservation of energy in consideration to figure out what is the velocity at that point. And then after figure out the velocity at that point, then you can just utilize whatever you learned in chapter 4 to find out the horizontal distance that the object would travel. Okay? Alrighty.